All right, howdy folks. Welcome back to the Professor Carbon YouTube channel. And here what we're going to do is talk through some reactions that are kind of classical functional group interconversions about aromatic groups. And so this is for those of you completing a chapter on electrophilic aromatic substitution, in addition to some of the functional group interconversions that are specific to the kind of places around the ring. As always, what I'm going to ask you to do is pause this video and spend some time to try to fill out the reactions I have shown on the screen here. And that way you'll become proficient on your own, and hopefully you'll be able to engage in a little bit more active learning instead of just listening to me give the answer to you. So please do pause right now and take a minute to fill this out. All right, welcome back. What I think we should do here is just talk about the top one. So I'm just going to zoom in up here. And this is a pretty classic reaction in organic synthesis. Hopefully it's one that's covered in your class. Here the kind of special clue that we're onto something fun is that we have this palladium carbon catalyst as well as some PPH3. And PPH3 for organic students is used really either in a Wittig reaction, or in this case it can be a ligand on palladium, which is what it's here for. And seeing palladium with one of these boronic acids should be a dead giveaway that we're going to do a Suzuki coupling. And the Suzuki coupling takes an aromatic nucleophile in the form of this aromatic boronic acid, and it couples it to an organic electrophile, and you make a direct bi-aryl bond. And so that one's kind of a fun one. So I'm just going to draw my starting material. And then this is the group that we're going to end up tagging over here. And so what I'm going to do is draw that bi-aryl bond. And then I'm going to have to think through what those groups around that boron were. And so if I put this carbon as being this carbon, then I have an ortho CH3. I'm just going to put CH3 there, and then para to it is the fluorine. And so I'm going to put a para fluorine up over here. And so then the bond that we would have made in the Suzuki is this one, sticking it together. All right, so fun reaction there. The next one here on BAT is, let's see here, potassium permanganate. Now that's a very strong oxidant. And one thing that we learn is that you can actually oxidize up benzylic methyl groups all the way to their acid carboxylate acid oxidation state in the action of permanganate is a very strong oxidant. And so conveniently enough, we do indeed have a carboxylic acid in the product. And so if we're going backwards or thinking retrosynthetically, what we'd want to do is imagine that being a simple methyl group. Now, for those of you that are perhaps a little bit on the imaginative side, really it could be any alkyl group here. So it need not be just methyl. Because we can fragment longer chains here as well, that R group could be anything. As long as it's a CH2 something, we can chew that something off. And indeed, I've had students put all kinds of clever things there with a note saying there's no way for me to mark it wrong. And of course I never do, because it's part of the fill in the blank answers. They can put in some starting material there that would give this product with permanganate. And so you could put something other than methyl there. Methyl is just the simplest one. All right, this one's kind of the opposite, because our starting material here has a ketone, and over here we've got a couple of CH2s. So if we're more comfortable with it, we can just draw in what these CH2s are here. And because of that, we're going to need a reduction, right? So the ketone we're going to need to reduce down to the CH2. And there's two kind of really classic reactions that we could put in here that would fill this criteria. The first of which is the Clemmensen reduction. And this is zinc with some mercury amalgam, and it often uses some HCl. So those are the conditions for the Clemmensen reduction. The other really famous one that we sometimes talk about is the Wolff-Kishner reduction, and that uses hydrazine, which is NH2, NH2. And then we use some base, so some sodium hydroxide and some heat. And so these are the conditions for the Wolff-Kishner. In this particular example, either of these sets of reagents should, in principle, complete the task of reducing an acetophenone or an aromatic ketone down to its CH2 unit. D here is probably going to be one of the most fun, and this is a fill in the product style problem, and there's a lot going on in the starting material. And for those of you that are new to this particular starting material or this particular reaction, this particular starting material is a dangerous one to manipulate in the lab. It's been known to explode, and so I would encourage you to be very safe if you're ever trying to actually generate this material. And to be perfectly honest, I would come up with a different way to do that reaction instead of making this stuff. But the reason it's so explosive is we can move those electrons down, move these electrons over, and kick off N2. And so the byproducts here are going to be carbon dioxide from up here, and then N2. And anytime that you're giving off multiple, well, any gas, not to mention 2 full moles of gas per mole of starting material, that's going to have a lot of energy associated with it. And remember, at ambient pressure, at ATP, 1 mole of gas is about 22.4 liters, so that's a pretty big volume. But 1 mole of something like water is only 18 grams. That's roughly 18 milliliters. So that's a pretty small volume. And so the expansion you get from going from a liquid to a gas is tremendous. And that's really what leads to the explosion here, is if this reaction runs away and it all goes at once, you have a lot of gas coming out and not a whole lot else. Now, ultimately, as the organic chemist, these aren't the fun parts to us. The fun parts to us are benzyne. And I'm just going to write this a little bit weird here. And this is kind of an unusual drawing, but that's where we get from the double bond up here. And now I'm going to take my liberty to push these arrows around to get us the other resonance structure of that benzene. And this now gets to benzyne, which is this. And if benzyne looks to you like something that should be absolutely wrong, I agree with you. It does look like something that's totally wrong. The downside is it's pretty well validated as a synthetic intermediate at this stage. And so please do just do a quick Google or Wikipedia search on benzyne all on your own. There's some really fun and exciting research going on utilizing benzyne. And so it's a very popular frontier in modern organic chemistry. Because it just looks so wrong, it turns out this double bond or triple bond is fantastic for the Diels-Alder reaction. And so that's where this butadiene is going to come in place. And so from here, we can engage in a Diels-Alder reaction. And so what we want to put in this box then is the product of a Diels-Alder reaction with benzyne. So that's kind of a fun reaction. All right, hopefully you enjoyed this really quick video here on a couple of aromatic reactions. Please do subscribe to the Professor Carbon YouTube channel. And for those of you that are big fans and you want access to these questions either in the blank format or filled out, please do just follow us on the Patreon webpage or give us a couple of likes down below in the video. Also tell your friends about it, and I'm more than happy to respond to those of you that leave comments. So cheers.